So you might have heard of the famous P equal to NP conjecture. It's a very famous conjecture, but as we'll see, it's also kind of ridiculous. Um, and on the topic of it being famous, there's actually $1 million prize for it. It was included in a list of most wanted problems of the next millennium, and it happens to be the only computer science problem on the list. So let's first get into why it's so ridiculous, and then if it's so ridiculous, then why is it so famous? So the conjecture has to do with algorithms and their runtime, and specifically their runtime in the worst case. So think of an algorithm like sorting an array, and think of how the time spent on the computer uh, depends on the size of the input. Here, in this case, it would be the size of the array. So you plot the input size on the x-axis, the algorithm runtime on the y-axis, and if you can find a polynomial that is always greater than your algorithm's runtime, then you say that in the worst case there is a polynomial time algorithm, and this kind of makes the concept of easiness concrete. If the runtime can be dominated by a polynomial, in the worst case, that means it's an easy problem. And this isn't always the case. A lot of times, the algorithm runs an exponential time, and you'll never find any polynomial that is always greater than an exponential function. So yeah, this makes the concept of easiness concrete, and this is what we need to define the conjecture further. Okay, so now let's understand the conjecture itself. So you have the class P, which is all problems where in the worst case you have an algorithm that solves them in polynomial time. So these are the easy peasy problems. As an example, sorting an array or telling if an array is sorted. You just loop through it, and obviously even in the worst case you can tell whether it's sorted or not, and this is polynomial time because it's just it's just a loop through the array. Then there's the class NP on top, which is problems that are verifiable in polynomial time, but we don't know if they're solvable in polynomial time or not. So as an example, you're given two graphs, and are the two graphs really the same graph in disguise? So here you have graph G and graph H, and they're really the same graph, but they're just arranged differently, they're labeled differently, and it's not trivial to tell that they're the same graph. But if someone gave you a mapping, that A in the first graph actually means vertex number 1 in the second graph, etc., then it would be very easy to verify. You would just make sure that all the edges line up, and yes, they are the same graph, or no, they are not the same graph. So verifying this is a polynomial time for sure, but if you weren't given this solution, then there's no known algorithm to do this in polynomial time. So that's the set NP. Another example of an NP problem is integer factorization, which all of modern cryptography depends on. And the P equal to NP conjecture says that there is no class NP. It's just P, and any problem verifiable in polynomial time is also solvable in polynomial time. I told you this was going to be ridiculous. So let's delve further into the ridiculousness of this conjecture. Again, it's saying any problem that you can verify easily, you can also solve easily. So let's translate that logically into a statement that a layperson could understand. So if you can appreciate a good car, that means you can build a good car as well. Now, if you made that statement to someone on the street, they would think you're being ridiculous. And often intuitions like these don't extend when you delve deeper into the subject, when you get to the level of researchers. But in this case, it does. So here's a famous quote by Scott Aaronson, a famous professor of computer science, who wrote a blog on why IP is probably not equal to NP. quoting, if P equal to NP, the world would be a profoundly different place than we usually assume it to be. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Everyone who could recognize a good investment strategy would be Warren Buffett. And then he goes on to ask, why is P versus NP even a reasonable question? Why even make a conjecture like this? Is it simply the case that someone made the conjecture and then you couldn't prove it isn't true? So, it just became famous for that reason. But then there's probably, millions of such conjectures that, you can't really prove, but they're, obviously, false or obviously true. So, why is this one so famous? So another way of framing this is, if we started civilization over, would we make this conjecture again? Or would an alien species make the same conjecture? And there's actually good reason to believe they would. And let's get into why this is, in fact, a very natural question to ask. There's a good reason it's so famous. So let's delve a bit into the history. In the late 60s, the field of computer science was taking off. It's kind of still taking off. And there were different problems people were coming up with that were becoming famous. Some of them you were finding polynomial solutions, others you weren't, and then eventually people were. But then there was always certain problems where no matter how hard people were trying, polynomial time solution just wasn't coming out. So if you can't solve a problem easily and you just try and try and try, and others in your field also try, at some point you start suspecting, is it even possible? Maybe there is no polynomial time solution to this problem. And then the next thought you have is, can I prove it's impossible? So I don't bother looking anymore, and I save others a bunch of time as well. And two researchers, Cook and Levine, tried to prove a particular problem, Boolean satisfiability was impossible. This problem is basically you try to solve a system of equations where the variables are all Boolean. They can take 1 or 0 values, and there's a bunch of OR conditions in between. And there was an exponential time solution to this problem, which was just brute force, but no polynomial time solution in sight. So they failed at this. They failed at proving that it was impossible to solve Boolean satisfiability in polynomial time. But they got another result that was maybe even more incredible. They showed that if you could solve this problem easily, you could solve any problem in the set NP. And again, remember the set NP is all problems verifiable in polynomial time. So all problems in NP could be mapped to this one problem, Boolean satisfiability, in polynomial time. So if you could solve this problem easily, then all those problems could also be solved in polynomial time, which was a pretty remarkable result. And then this class NP complete was born, where you had at first just one problem where everything in NP could be reduced to it, and then that you started getting more and more problems like that. And this was a major development, showing that solving this one problem would make the whole set NP collapse. So now you had at first just this Boolean satisfiability as a single problem that everything in NP could be collapsed to, but then this set started growing. Other problems were also shown to have this property, and the way you do that is you show that Boolean satisfiability can be reduced to these other problems in polynomial time, and then you show that all the NP problems can be reduced to those problems in polynomial time as well, because you go from them to Boolean satisfiability and from there to all these other problems. So this set started expanding, and then the name of this new set was NP complete, because it would kind of complete all the NP problems. And this is where the conjecture came from. What if someone someday solved just one NP-complete problem? That would immediately collapse all of these three sets into one set, which would be just a P. All these problems would be solvable in polynomial time. And that is why this conjecture is famous, because it's the only thing standing between us and a proof that all of these problems don't have any polynomial time solution. So we've managed to show that if a polynomial time solution exists, then this ridiculous conjecture would also be true, but we haven't quite proved that this conjecture is in fact not true beyond any reasonable doubt.